Hi guys, this is the EdExcel A-Level Maths Paper 1 from the June 2019 series. Let's get straight into it. So, examiner report wise, this was the first pure Mathematics 1 paper under the new specification which tested the full cohort of candidates. The paper had many straightforward and accessible questions as well as more demanding ones that stretched the more able candidates, and you can read about which questions those are. The performance of candidates on topics that were new to the specification were mixed, and you can read about that. Generally, candidates had difficulty on questions that demanded an explanation. This is something that will improve over the lifetime of the specification as both candidates and teachers adjust to these new demands. Question number 1. We have f of x equaling 3x cubed plus 2ax squared minus 4x plus 5a, and given that x plus 3 is a factor of f of x, we have to find the value of the constant a. Now, if x plus 3 is a factor of f of x, we begin with the x plus 3 equaling 0, which implies x is equal to minus 3. And with this, we can therefore say f of minus 3, that's equal to 0. So, substituting minus 3 for x and then setting f of minus 3 equal to 0, we can arrive at a linear equation in A and then solve for A. So we have 3 lots of minus 3 cubed plus 2A lots of minus 3 squared minus 4 lots of minus 3 plus 5A. This is all equal to 0. So here we have minus 81 plus 18a plus 12 plus 5a equals 0. We see that 23a, that's equal to 69, and therefore a is equal to 3. And therefore, knowing that a is equal to 3, we can say in conclusion, f of x, that's equal to 3x cubed. Now we have 2ax squared, so 2 times by a, that would be 6. So we have 6x squared minus 4x plus 5a, so we have 5 times by 3, which is 15. Question number 1. This proved to be a very suitable start to the paper. Most candidates used the factor theorem and produced an equation in A by setting f of minus 3 equal to 0. Most could then solve their linear equation in A and find its value, and that's exactly what we did. Candidates who used this method generally went on to score more full marks. Common mistakes tended to be arithmetic or sign errors, for example, not finding the cube root of minus 3 accurately in the first term. And I always say, put it in brackets and then substitute into your calculator. That would help to ensure that you're not making sign errors. Other methods that were seen but were generally less efficient and not as effective, those candidates that started with x plus 3 lots of ax squared plus bx plus c and equated coefficients were generally successful. However, those candidates that tried to solve this problem using long division generally made errors and did not score highly. It was rare to see candidates scoring 0 on this question. Question number 2. We've got figure 1, which shows a plot of part of the curve with the equation y equals cos x, where x is measured in radians. And on diagram 1, on the opposite page, we've got a copy of figure 1, as we see over here. We have to use diagram 1 to show why the equation cos x minus 2x minus 1/2 equals 0 has only one real root, giving a reason for your answer. Okay. So for part A, we begin with cos x minus 2x minus 1/2 equals 0. And if we take this minus 2x minus 1/2 to the other side, we have cos x equals 2x plus 1/2. And so far, drawn for us, we've got cos x. And if we draw the line 2x plus 1/2, you'd find that we have 1 point of intersection. So let's draw 2x plus 1/2 on this diagram. Drawing 2x plus 1, we have this line over here. So we've got this red line over here, 2x plus 1, and here already given to us, we have the graph of cos x. And therefore, what you'd hopefully find is there's 1 point of intersection, and therefore there's only one real root. So let's just write that down. So we've got 1 point of intersection that was shown in green over here, and therefore we have only one real root. Now for part B, given that the root of the equation is alpha and that alpha is small, we have to use the small angle approximation for cos x to estimate the value of alpha to 3 decimal places. Well, first of all, we would have to find what the small angle approximation is for cos x. And if you look in the formula book, the small angle approximation, that's shown here. Cos theta is approximately 1 minus theta squared over 2. So we can use that angle approximation and replace that with what we have over here. So for part B, using the small angle approximation, we have 1 minus 1/2 x squared minus 2x minus 1/2 equals 0. And if we multiply through by 2, we have 2 minus x squared minus 4x minus 1 equals 0. And if we tidy this up a bit, we have x squared plus 4x minus 1 equals 0. And if we solve this equation, of course we can use our calculator. So go to the menu, equation/function option. We have a polynomial of degree 2. The coefficients are 1, 4, minus 1. You'd find we have a root of x equaling 0.236, etc. And our second root, we have minus 4.236, etc. And we know that theta is small, and therefore we can conclude that x equals 0.236 to, if we go back to 3 decimal places, is the only solution. Okay. Question number 2, examiner report wise. This question proved to be more challenging for a number of candidates, although many were still able to score full marks. In part A, where we had to use the diagram to show why this equation equals 0 has only one real root, it was important for candidates to pay attention to the scale of the graph. Did I do that? Yes, I did. Most candidates who did draw a straight line graph were able to make the link between one point of intersection and one real root to the equation. However, a significant minority of these were unable to construct the correct single line graph with enough accuracy to gain both marks for this part of the question. For the next part of the question, where we had to use the small angle approximation, almost all candidates were able to write down the small angle approximation for cos x, even if they were unable to use it in order to answer the question. Most candidates did substitute correctly into the equation in order to gain a quadratic equation, although some did contain a mixture of variables. Sign errors sometimes occurred at this stage, and the weakest candidates were unable to deal correctly with resulting fractions. In order to simplify the equation, many candidates appear to be using calculators in order to solve quadratics, and in this question this usually resulted in full marks. The final mark was lost by some candidates who correctly solved the quadratic equation but gave both roots as their final answer. Remember, there's only one real root and we're looking at the small angle from it. Question number 3. We have y equals 5x squared plus 10x divided by x plus 1 all squared, where x doesn't equal minus 1. And for part A, we have to show that dy over dx equals a over x plus 1 to the power of n, where a and n are constants to be found. Now, you'll notice here we have a function divided by another function. And if we go to the formula book, that's shown here. When we have a function over another function, we'd have to use the quotient rule. When we differentiate f of x divided by g of x, the result of this is f dash times by g minus f multiplied by g dash over g squared, where f and g are both functions of x. Now, I like to use the notation u and v, and u dash and v dash. And for part A, u is the thing at the top, v is the thing at the bottom. So we have u equals 5x squared plus 10x, and we have u dash, therefore, which is equal to 10x plus 10, and we have v, which is equal to x plus 1 all squared, and by the chain rule, v dash, well, here we can use the bracket rule, so we have 2 lots of x plus 1 to the power of 1 times by the derivative of the bracket, which is 1, so we are left with 2 lots of x plus 1. And therefore, dy over dx, that's equal to v times by u dash minus u times by v dash divided by v squared. And if we substitute in what we know, we have v, which is x plus 1 all squared, times by u dash, which is 10x plus 10, minus u, which is 5x squared plus 10x, lots of v dash, which is 2 lots of x plus 1. And we then divide this result by v squared, so we have x plus 1 all squared squared. And if we tidy all this up, we have the following. Well, here, where we have the 10x plus 10, I can factorise out a 10. So we have 10 lots of x plus 1. This is the same as 10x plus 10. And then we multiply this by x plus 1 all squared, and then we subtract off. Well, considering the 5x squared plus 10x, we can factorise out from that a 5x. So we have 5x lots of x plus 2. So 5x lots of x plus 2 gives the 5x squared plus 10x, and then we still multiply this by 2 lots of x plus 1. And then on the bottom, x plus 1 all squared, well here we have a power raised to another power, so we multiply the powers. So on the bottom we have x plus 1 to the power of 4. Okay, and if we tidy this up a bit further, here hopefully you can see we have 10 lots of x plus 1, lots of, if I just write this neatly, x plus 1 lots of x plus 1 squared, minus, well, 5x times by 2, that's 10x. So we have 10x lots of x plus 2 lots of x plus 1. And on the bottom, we have x plus 1 to the power of 4. Okay. So if we continue to tidy all this up, we have, hopefully you can see we have 10 lots of x plus 1 as a common factor, and inside this big bracket we have x plus 1 all squared minus x lots of x plus 2, close big bracket. And on the bottom we have x plus 1 to the power of 4. And hopefully you can see the x plus 1 here cancels with this fourth power to give us a third power. So we have 10 lots of what's in the bracket here. Now x plus 1 all squared, that's x squared plus 2x plus 1, and then we subtract off x times by x, which is x squared, and then we also subtract off x times by 2, which is 2x. And on the bottom we have the x plus 1 cubed. Now if we tidy all this up, x squared minus x squared gives a 0x squared, 2x minus 2x, that gives a 0x, so we have 10 times by 1, which is simply 10. So we have 10 over x plus 1 cubed. And therefore we can see that a, that's equal to 10, and n, that's equal to 3. And now for part B, hence deduce the range of values for x for which dy over dx is less than 0. And for part B, that's quite straightforward. For dy over dx being less than 0, what we have is this thing over here, the 10 over the x plus 1 cubed being less than 0. Okay? Now, for this to be less than 0, the thing at the bottom has to be negative. The reason being, let's just write it down actually. Since 10 is greater than 0, it follows from here that x plus 1 all cubed must be less than 0. Hopefully that makes sense, because if we have something positive, that's a 10, divided by something negative, which is the x plus 1 all cubed, then positive divided by negative will be negative. In other words, positive divided by negative, that's less than 0. So we're solving the inequality x plus 1 all cubed is less than 0. And if we cube root both sides, we have x plus 1 being less than 0, and therefore x is less than minus 1. Question number 3. For part A we had to use the quotient rule. This was an accessible question for most candidates, but the second half of part A did discriminate at all levels. In part A, candidates generally recognised the need to use the quotient or product rule and were successful at differentiating for the first 2 marks. The most common mistake was forgetting to square the denominator, with incorrect order of terms in the numerator being less common. Candidates should also be reminded to quote formula before attempting to use it, as they may still gain method marks for this, even if there are slips in its application. Omission of brackets in terms in the numerator was also common, but this recovered in working. However, it would benefit candidates to be careful in the use of brackets. Having achieved a derivative, attempting to simplify to the required form proved difficult for many candidates. Many did not realise that they could factorise the x plus 1 out early and instead expanded fully, simplified and then factorised again to cancel in the last step. This wasted valuable time, and it was during this process that many errors usually occurred. The alternative method of simplifying the fraction before differentiating was less common, with usually poor attempts at partial fractions being applied leading to error. Those who successfully simplified the fraction almost always went to achieve the correct answer, and there's no point of using partial fractions as well because it's only worth 4 marks. Nearly all candidates who were correct in part A achieved the mark for part B, including many who had failed to cancel the x plus 1. Indeed, there were many candidates where a correct answer to part B was seen following incorrect work in A, presumably due to a calculator to plot and inspect the graph. Okay, so I'm guessing that's on about those who used a graphical calculator. Question number 4. We have to find the first 3 terms in ascending powers of x of the binomial expansion of 1 over the square root of 4 minus x, giving each coefficient in its simplest form. Well, for part A, we can rewrite this 1 over the square root of 4 minus x as 4 minus x to the power of minus 1/2. And this is equivalent to the following. We have 4 times by 1 minus 1/4 x all to the power of minus 1/2. So this is equivalent to 4 to the power of minus 1/2 lots of 1 minus 1/4 x to the power of minus 1/2. And we can tidy this up a bit. 4 to the power of minus 1/2, that's simply 1/2. So we have 1/2 lots of 1 minus 1/4 to the power of minus 1/2. Now, if we take a look in the formula book, you'd find here for a binomial series, we have this formula over here. So we can use this formula to find out what this expansion is approximately equal to. Okay, so what we have over here then is this expansion being approximately equal to 1/2 lots of 1 plus minus 1/2 lots of minus 1/4 x divided by 1 factorial. And then we have, for our next term, minus 1/2 lots of minus 1/2 minus 1 lots of minus 1/4 x squared divided by 2 factorial. We could continue, but in the question we just have to find the first 3 terms. So we've got our first term, our second term, and our third term. And if we tidy all this up a bit, we have 1/2 lots of 1, and then here we have minus 1/2 times by minus 1/4 x. That would be positive x over 8. And then here we have minus 1/2 times by minus 3 over 2 times by 1 over 16 divided by 2. So that would be 3 over 128, and then we times this by x squared. So we add on 3x squared over 128, and of course we could continue. But in the question, again, we were told to only find the first 3 terms of the expansion. And if I multiply this 1/2 into the bracket, we have 1/2 plus x over 16 plus 3x squared over 256. Okay, and of course we could continue with our expansion. Okay, so that's part A done. Now for part B, the expansion can be used to find an approximation to root 2. Possible values of x that could be substituted into this expansion are x equals minus 14, because once you substitute into the expansion you get root 2 over 6. X equals 2, because once you substitute this into the expansion you get root 2 over 2. And you can also substitute in x equals minus 1/2, because once you substitute into the expansion you end up with root 2 over 3. Without evaluating your expansion, state, giving a reason, which of the 3 values of x should not be used. Well, if we consider this expansion, considering this 1 minus 1/4 x, the range of values for which this expansion is valid, for the first part of part B, we have the mod of x over 4 being less than 1. In other words, the mod of x is less than 14. And therefore, if we consider this x equals minus 14, that does not satisfy this condition. And therefore, we can state that we must not use, so don't use x equals minus 14. The reason being, x can take values between minus 4 and 4. And now for the next part, state, giving a reason, which of the 3 values of x would lead to the most accurate approximation to root 2. And that's quite easy. We can either choose the x equals 2 or the x equals minus 1/2. Now the x equals minus 1/2, that's closest to 0, and therefore x equals minus 1/2 will give the most accurate approximation. Let's just write that down. So x equals minus 1/2 gives the most accurate approximation because it's closest to 0. Question number 4. This was concerning the binomial expansion. The vast majority of candidates did well in part A, securing most or all of the marks available. They appreciated the need to rewrite the expression with a negative power and dealt correctly with the factorization. The binomial expansion itself was also correctly executed, and careful working ensured that there were relatively few slips in powers or signage. Common errors include included bracketing errors seen with minus x squared over 4 in the third term rather than minus x over 4 all squared, or failing to correctly combine the factored out 4 to the minus a half in the expansion 1 plus x over 8 plus 3x squared over 1 to 8. In part B, this caused more difficulty. In the first part, many candidates appeared to realise that the question was linked to the range of valid x values, and the correct answer, x equals minus 14, was selected most often. To gain this mark, however, the correct answer and a valid reason needed to be given. Examples of valid reasons were the expansion is only valid for the mod of x being less than 4, and the expansion is not valid for x equals minus 14, as the mod of minus 14 is greater than 4. The next part, only a small proportion of candidates realised that the expansion is more accurate for values of x closest to 0. Many resorted to using the 3 values given and compared the results to the exact value of root 2, or else stating that the answer was 2 as it was closest to the value of it. Question number 5. F of x equals 2x squared plus 4x plus 9, where x is a real number, and we have to write f of x in the form a lots of x plus b all squared plus c, where a, b and c are integers to be found. Now, this form over here is in complete the square form, so we would have to complete the square for f of x. So for part A, we begin with the 2x squared plus 4x plus 9, and if we factorise out a 2 from the first two terms, we have 2 lots of x squared plus 2x plus the 9, and we now need to complete the square of what's in this big bracket. So we have 2 lots of x plus 1 all squared minus the 1 squared, close big bracket, plus 9. So if we tidy all this up, we have 2 lots of x plus 1 all squared, and then we have 2 minus 1, so 2 times by minus 1, which is minus 2, and then plus the 9. And therefore, we can conclude f of x, that's equal to 2 lots of x plus 1 all squared plus 7. Now for part B, we have to sketch the curve with the equation y equals f of x, showing any points of intersection with the coordinate axis and the coordinates of any turning point. Well, first of all, for part B, when x is equal to 0, we can see that f of 0, that's equal to 2 lots of 0 squared, which is 0, plus 4 lots of 0, which is 0, and then we add on the 9. So f of 0, that's equal to 9. And we see that the turning point, if we consider this complete the square form, the turning point, that would be minus 1, 7. And therefore, because 7 is above the x-axis, we can therefore conclude that the graph f of x does not cross the x-axis. Okay? So we've got the following graph over here. We've got our minimum point minus 1, 7, and we've got where the graph crosses the y-axis, which is at 0, 9. Of course, the graph does not cross the x-axis as shown. Now for part C, for the first part, we have to describe fully the transformation that maps the curve with equation y equals f of x onto the curve with equation y equals g of x, where g of x is equal to 2 lots of x minus 2 all squared plus 4x minus 3, where x is a real number. So there's a couple of ways to think about this, but essentially what we're doing in this question, for the first part of part C, we're going from 2 lots of x plus 1 all squared plus 7 to 2 lots of x minus 2 all squared plus 4x minus 3. And what we can do is we can simplify all this and write it in complete the square form and then compare it to what f of x is. So essentially we have over here f of x, and here we have g of x. And if we tidy this up, well, we have 2 lots of x minus 2 all squared, so that would be x squared minus 4x plus 4, and then we have this 4x minus 3 as well. And if we tidy all this up, well, we have 2x squared, and then we have 2 times by minus 4x, that's minus 8x, plus another 4x, that would be minus 4x. And then we have 2 times by 4, which is 8, minus the 3, that would be 5. Okay, so if we complete the square with this, we can compare f of x with g of x. So completing the square, we have 2 lots of x squared minus 2x, close big bracket, plus the 5. So we have 2 lots of x minus 1 all squared minus 1 squared, close big bracket, plus the 5. And if we multiply the 2 into the bracket and simplify, you'd find we have 2 lots of x minus 1 all squared. Now 2 times by minus 1, that's minus 1, plus the 5. Sorry, 2 times by minus 1, that's minus 2, plus the 5, that's 3. So if we compare the 2 lots of x plus 1 all squared plus 7 with the 2 lots of x minus 1 all squared plus 3, you can hopefully see that in terms of the x, we've subtracted 2, and in terms of this 7 to the 3, we've subtracted 4. So we're going from f of x to f of x minus 2 minus 4. I'll just repeat that. 1 minus 2, that gives the minus 1, and the 7 minus the 4, that gives the 3. And we can therefore conclude that we have a translation by vector 2 minus 4. Okay, so let's write that out neatly. We have a translation by vector 2 minus 4. Now for the next part, slightly more tricky, we have to find the range of the function h of x equals 21 over 2x squared plus 4x plus 9. Now this 2x squared plus 4x plus 9 is what we had over here, that's f of x. And f of x in complete the square form, that was 2 lots of x plus 1 all squared plus 7. Essentially what we have over here is the following. We have h of x, which is equal to 21 over 2x squared plus 4x plus 9. So we have 21 over f of x. Hopefully that should be quite straightforward. And if you look at the graph that we drew for part B, hopefully you can recognize that the range of f of x, that would be f of x is greater or equal to 7. So let's just write that down. The range of f of x, that would be f of x is greater or equal to 7. And therefore, the smallest value we need to substitute in to h of x would be the 7. because that's the minimum point of x. So therefore, let's just write that down. The smallest value to sub into h of x is 7. Okay, so what you'd also notice as well, as f of x gets bigger than 7, h of x will get smaller and smaller. Let's just illustrate this. We have 21 divided by 7. That would be one of the limits of the range of h of x. And as we see, as we increase this f of x to something bigger than 7, say 700, we get something smaller. And if we continue increasing, we get something much smaller. Essentially, as f of x tends towards infinity, and that makes sense because f of x is going to infinity, we see then that h of x tends towards 0. And that makes sense. Now let's see what happens when f of x is equal to 7. When f of x equals 7, h of x, that would equal 21 divided by 7, which is 3. And therefore, what we see then, the range of h of x, we have 0, which is less than or equal to h of x, which is less than or equal to 3. Okay. Question 5. This question on completing the square and then quadratic function was accessible to all, especially in the first 6 marks. Part C was more demanding, but there were some excellent responses here. Part A was very straightforward and many candidates were able to write down the answer without any difficulty. Although errors were rare, one common incorrect answer was 2 lots of x plus 1 all squared plus 8. I don't know how you'd get that, if I'm honest. Part B was equally straightforward, even for candidates who did not achieve the correct result in Part A. Many used the form of a lots of x plus b all squared plus c, or their graphical calculators to produce accurate and well-drawn curves. Marks were lost here when candidates drew V-shaped curves or had incorrectly placed turning points. As stated earlier, Part C was a lot more demanding. Rather strangely, Part I was found more accessible than Part II. Many candidates achieved the new curve and compared the position of the turning point, noting that -1, 7 had moved to 1, 3. And if I go and have a look at my solution, that's what I did. Disappointingly, a rather sizable majority could only describe this movement as a transformation rather than a translation. And I thought if you write this stage over here, it becomes quite obvious that we have a translation. Fewer candidates could then use the form h of x equals 21 over 2 lots of x plus 1 all squared plus 7 to find the range of the function. Many resorted to substituting x equals 0, producing a range with y equals 21 over 9 as one of the limits. Common incorrect answers for the range of h, scoring 1 mark, were h of x being greater or equal to 3, or 0, which is less than f of x, which is less than or equal to 3. Question number 6, we have to solve for part A. For theta being in between -180 and 180, the equation 5 sine 2 theta equals 9 tan theta, giving answers where necessary to 1 decimal place. So for part A, we begin with the 5 times by the sine of 2 theta equaling 9 times by tan theta, and sine 2 theta, that's the same as 2 sine theta cos theta. It's a double angle formula which you should know. And tan theta, that's the same as sine theta over cos theta. Okay? And tidying all this up, we have 10 times by sine theta cos theta, that's equal to 9 times by sine theta over cos theta. And if we multiply both sides by cos theta, you'd find we have 10 times by sine theta cos squared theta, that's equal to 9 times by sine theta. And if we take everything over to one side, we have 10 times by sine theta times by cos theta minus 9 times by sine theta. This is equal to 0. And hopefully you can see we have a sine theta which is common to both. So we have sine theta times by 10 cos squared theta minus 9. And all this is equal to 0. Now, solving this, either the first bit is equal to 0 or the second bit is equal to 0. So what we see over here then is sine theta, that's equal to 0, or 10 cos squared theta minus 9, that's equal to 0. So sine theta, that's equal to 0, or we have cos theta, that's equal to plus minus 9 over 10 square rooted. Okay, and at this point, drawing a graph will help find the solutions. So let's do that. So having drawn the graphs, well, we've got in blue the graph of sine x, and in red we've got the graph of cos x. And we've got sine x equaling 0, and if we consider the solutions for that, well, sine x equals 0 at minus 180, 0 and 180. So let's just write that down. We've got solutions of theta equaling plus minus 180 and also 0. And if we consider the solutions for cos theta equaling plus minus the square root of 9 over 10, then what you'd find is we've got a solution here, that's one of them. So we've got a solution here, we've got a solution here, here, and also here. Okay, so if we now find out what those intersection points are, well, we've got the inverse cosine of the square root of 9 over 10. So we've got a solution of 18.4, that's here, and then by symmetry we've also got the minus 18.4. So let's add those solutions in. We've got plus minus 18.4, and also we've got the negative of this, so we've got 161.6. okay, so that's this solution, and by symmetry we've also got that over here. So therefore we've also got a solution of plus minus 161.6. And don't forget, we've got degrees. Okay, and all these are to 1 decimal place. Okay, so now for part B. For part B, we have to deduce the smallest positive solution to the equation 5 sine of 2x minus 50 equals 9 times by tan of x minus 25. So if we use part A, using part A, what we have over here is the sine of x minus 25, lots of 10 times by the cosine, 10 times by the cosine of x minus 25 squared minus the 9, and this is equal to 0. Okay, so what you can hopefully see then, perhaps if we highlight it, we've got theta, which has been replaced with x minus 25. So let's just write that down. In other words, what we see is that theta, that's equal to x minus 25. In other words, x is equal to theta plus 25. And the smallest value of x, that would occur when theta is equal to minus 18.4. Because remember, in the question, we're looking for the smallest positive solution. So obviously, we're not going to be considering this plus minus 180, because once we add 25 to it, it's still too big. The 0 we could consider, but again, we won't have something which is small. We could consider this 161.6, again that would be too big. But if we consider this minus 18.4, adding 25 to it will give us the smallest solution. And if you want, you can actually work out what x would be from here, and then reject all the rest of the values apart from one of them. But hopefully it would be quicker to recognize that if we have minus 18.4 and add 25 to it, that would be the smallest value of x to have. So let's just write that down. The smallest positive value of x, that occurs when theta, that's equal to minus 18.4 degrees. And therefore, what we can see then is x is equal to minus 18.4 plus the 25 from here, and therefore x, that's equal to 6.6 degrees to 1 decimal place. So this is our smallest positive solution. Okay. Question number 6. This was a well attempted question with most candidates able to score over half of the marks available. In part A, the correct identities were all well known and efficiently used in order to obtain an equation in one function. Almost all candidates who reached this stage were then able to proceed to find at least one correct angle. It was clear from the graphs and diagrams sketched by most candidates that they had been taught to look for all angles in the required range, and many were able to give all 4 of the angles needed. Only a minority of candidates identified 0 and plus minus 180 as solutions to the equations. Most candidates divided through by sine theta or cos theta and failed to identify any of these values. And I think it becomes quite obvious from this line why we have sine theta equals 0 and then having those 0 and 180 degrees as our answers. And obviously drawing a sketch will help identify the correct angles you need. For part B, a significant number used 2x minus 50 equals theta rather than x minus 25 equals theta. Of those who used one of their solutions in part A, the majority then proceeded to the correct final answer. Although a significant number did not give the smallest positive solution to the equation, this was usually due to the fact that they used their smallest positive solution in part A, in other words the 18.4, in the equation, not realizing that they needed to use the minus 18.4, and we discussed. Question number 7. In a simple model, the value v pounds of a car depends on its age t in years. The following information is available for car A. So its value when new is £20,000. Its value after 1 year is £16,000. For part A, we have to use an exponential model to form, for car A, a possible equation linking v with t. So for part A, I hope it's quite obvious that v is equal to a times by k to the power of t. Okay? And what you see over here is an exponential model. Now, we know that when t equals 0, v is equal to 20,000, and using this information, we can find out the value of a. So, we have here, if we quickly underline this, we have 20,000 equals a times by k to the power of 0. K to the power of 0, that's just 1, and therefore a, that's equal to 20,000. Now, when t is equal to 1, so after 1 year, v, that's equal to 16,000. So with this information, let's see what we get. We have 16,000 equals a, which is 20,000 multiplied by k to the power of 1. And if we divide 16,000 by 20,000, hopefully you can see k is equal to 0.8. And therefore, we can conclude v, that's equal to 20,000 times by 0.8 to the power of t. Now, for part B, the value of car A is monitored over a 10-year period. Its value after 10 years is £2,000. We have to evaluate the reliability of your model in light of this information. Well, let's see with our model how much the car would be worth after 10 years. So for part B, after 10 years, so when t equals 10, let's see what v is. V, that's equal to 20,000 multiplied by 0.8 to the power of 10, and working this out, we have 20,000 multiplied by 0.8 to the power of 10. That would be 2147.48. And this over here is approximately £2,000, and therefore the model is valid. Let's just write that down. So the model is valid because this value over here is close to £2,000. And now for part C, the following information is available for car B. It has the same value when new as car A. Its value depreciates more slowly than that of car A. We have to explain how you would adapt the equation found in A so that it could be used to model the value of car B. Now, if the car depreciates more slowly than that of car A, then our k over here must be bigger than 0.8. So let's just write that down. So we need to increase the value of k such that k is greater than 0. Question 7. It was pleasing to see that most candidates attempted to form an exponential model using a suitable equation. This is one of the new topics in the specification, and candidates who didn't gain any marks on this question generally did so because they did not attempt it, or that they tried to use a non-exponential model. For part A, v equals a r to the power of t or v equals a e to the power of kt were the more popular types of correct model that candidates opted for. However, some methods were often muddled and poorly shown, but many candidates who used a correct model were able to proceed to obtain correct values for their constants. The candidates who used the model v equals a e to the power of kt frequently gave the constant k as a logarithm, and errors sometimes occurred with the sign of this constant. Errors in calculating constants with the model v equals ar to the power of t often occurred when candidates used v equals ar to the power of t minus 1 instead. For part B, candidates who correctly answered part A usually understood that for this selection they needed to substitute t equals 10 into their model, and most were able to do this. Many candidates then proceeded to make a sensible comparison of the value gained by their model with the actual value in order to comment on the model's reliability, sometimes calculating and commenting on a percentage error. The final mark, however, was frequently lost because their answers were too vague, without a clear comparison or assessment of reliability being made. Some candidates appeared to think that a model was only acceptable if it gave the exact real value. For part C, most candidates who attempted part C understood which of their two constants would need to be altered, although marks were lost either because the answer given just said the constant needed to be changed, or because they wrongly identified whether the constant needed to be decreased or increased. This was more of a difficulty for those candidates who had used the model v equals a e to the power of kt, because candidates were often dealing with negative constants or constants given as logs, so the phrases were not always mathematically correct. An example was often useful to convey what candidates meant where there was ambiguity. Candidates who had gone with the model v equals ar to the power of t were less likely to make an error in judging whether their constant should increase or decrease. Question number 8. We have figure 2, which shows a sketch of part of the curve with the equation y equals x lots of x plus 2 lots of x minus 4. The region R1, shown shaded in figure 2, is bounded by the curve and the negative x-axis. We have to show that the exact area of R1 is 20/3. Now, for part A, it's quite straightforward what we do. We wish to integrate between this point here and x equals 0. And if we expand and simplify our equation for y, we can then use that to integrate. So, for part A, we have y equals x lots of x plus 2 lots of x minus 4, and if we expand and simplify, we have x lots of x squared minus 2x minus 8, which is the same as x cubed minus 2x squared minus 8x. Okay? And when y is equal to 0, we have 0 equals x lots of x plus 2 lots of x minus 4. In other words, where the curve crosses the x-axis, that would be at the point 0, minus 2, and 4. So let's add this to the diagram. The curve crosses the x-axis at minus 2, the origin O, and the point x equals 4. Okay? And we wish to find the exact area of R1. And for us to do this, we would have to integrate between minus 2 and 0 this curve. So the area of R1, that will equal the integral from minus 2 to 0 of x cubed minus 2x squared minus 8x with respect to x. So integrating this, well, integrating x cubed, we end up with 1/4 x to the 4. Integrating 2x squared, we end up with 2/3 x cubed, and integrating minus 8x, we end up with minus 4x squared. And we wish to evaluate this between minus 2 and 0. So working this out, for our upper limit, we have 1/4 lots of 0 to the 4 minus 2/3 lots of 0 cubed minus 4 lots of 0 squared. For our lower limit, we have 1/4 lots of minus 2 to the 4 minus 2/3 lots of minus 2 cubed minus 4 lots of minus 2 squared. And if we work all this out, indeed we do get 20/3 units squared. Okay, and now for part B, the region R2, also shown shaded in figure 2, is bounded by the curve the positive x-axis and the line with equation x equals b, where b is a positive constant and b is in between 0 and 4. Given that the area of R1 is equal to the area of R2, we have to verify that b satisfies the equation b plus 2 all squared lots of 3b squared minus 20b plus 20 equals 0. Now, if R2 is below the x-axis, the integral of R2 will be negative. We know that the area of R1 is equal to the area of R2, so R1, the area of that is 20/3. The area of R2, that's also 20/3. But in terms of the integral of R2, that will be negative because we're below the x-axis. Let's write that down for part B. R2 is below the x-axis, and therefore the integral between 0 and b, that would be negative. Okay, so with that, let's integrate between 0 and b. So we have R2, the integral of R2, that will equal, well, we're integrating between 0 and b, and we're integrating x cubed minus 2x squared minus 8x with respect to x. And we know that this integral will be negative. It will be minus 20/3. Remember, the area of R1 and R2 are the same. So given that R1 equals R2, we can therefore conclude that the integral of R2 will be negative. So working this out, we have 1/4 x to the 4 minus 2/3 x cubed minus 4x squared between 0 and b. That's equal to minus 20 over 3. And of course, for our upper limit, we would end up with 1/4 b to the 4 minus 2/3 b cubed minus 4 b squared. Obviously for our lower limit, substituting 0 into here, we end up with 0. So all this is equal to minus 20 over 3. So slight bit of rearranging, we have 1/4 b to the 4 minus 2/3 b cubed minus 4b squared plus 20 over 3. That's all equal to 0. And if we multiply through by 12, we end up with 3b to the 4 minus 8b cubed minus 48b squared plus 80 equals 0. Now, if we divide this result here by b plus 2 all squared and end up with 3b squared minus 20b plus 20, then of course we can verify that b satisfies this equation. It's a bit of a weird question actually if we think about it, but that's probably the best way to answer this question. So maybe if I write this down in a different colour. So we've got this b plus 2 squared, which is equivalent to b squared plus 4b plus 4. If I call this, well, the way we can do this actually is we can do 3b to the 4 minus 8b cubed minus 48b squared plus 80 divided by b squared plus 4b plus 4. And if we do that, we have the following. So let's think about a good way to write this. Well, we've got this 3b to the 4 minus 8b cubed minus 48b squared, and I'm just going to write in plus 0b plus 80. It makes my polynomial division a bit easier. And we're dividing this by b squared plus 4b plus 4. Okay, so if we work this out, well, this is where it gets a bit complicated actually. 3b to the 4 divided by b squared, that would be 3b squared. So we put the 3b squared here, and 3b squared multiplied by this, we end up with 3b to the 4 plus 12b cubed plus 12b squared. And subtracting these, we end up with minus 20b cubed because 3b to the 4 minus 3b to the 4, that would be 0. And here we end up with minus 60b squared. We bring these two down, so we have plus 0b plus 80. Okay, and minus 20b cubed divided by b squared, that would be minus 20b. So here we have minus 20b, and multiply this by this, we end up here with minus 20b cubed minus 80b squared minus 80b. And if we subtract these, so subtracting these together, we end up here with 20b squared plus 80b plus 80, and therefore 20b squared divided by b squared, that would be 20, and 20 times by this result here, we have 20b squared plus 80b plus 80. And if we subtract these two, we end up with 0. So let's just make it clear that we're subtracting these from each other. So we have a remainder of 0, and therefore we can conclude over here that 3b to the 4 minus 8b cubed minus 48b squared plus 80 divided by b to the divided by b squared plus 4b plus 2. This of course is equivalent to 3b squared minus 20b plus 20. And therefore, in conclusion, we have b plus 2 all squared, lots of 3b squared minus 20b plus 20. That's equivalent to 3b to the 4 minus 8b cubed minus 48b squared plus 80. Okay, so therefore that's what we wanted to show. A bit of a complicated question to think about in terms of verifying the result, but hopefully that was the easiest way to verify the result, and that's through dividing the polynomials by each other. Okay, so now for part C, the roots of the equation 3b squared minus 20b plus 20 equals 0 are 1.225 and 5.442 to 3 decimal places, and the value of b is therefore 1.225 to 3 decimal places, and we have to explain with the aid of a diagram the significance of the root 5.442. Okay. Now this is actually quite a difficult question to think about. So far what we've seen, if R1 equals R2, if the areas are equal, then the net integral will be 0, because we've got a positive integral here, a negative integral here, and therefore the total integral will be 0. Now if b equals 5 point something, that will be to the right over here, so let's just add this in. If we have a different value of b, say over here, we have 5 point, let's just check the value, 5.442. What we're doing in this question is explaining the significance of this 5.442, and here of course is where we have the 1.225. essentially, it's quite difficult to spot, but what we're saying over here is R1 equals R2. We were told that in the question over here. And because of that, the net integral will be 0. So in other words, if b isn't 1.225, let's suppose instead it's 5.442. The net integral, we still should know should be 0 because R1 equals R2. Okay? And for that to happen, the area above the x-axis must be equal to the area below the x-axis. So if instead we have b equaling 5.442, we have this bit over here. Okay, this bit here is equal to what we have over here. In other words, the area above the x-axis is equal to the area below the x-axis. So let's just put that down into some sort of decent wording. So if the area of R1 is equal to the area of R2, then the net integral must be 0. And therefore, because the net integral is 0, the area above the x-axis is the same as the area below the x-axis. And on the diagram, of course, you must recognize that 5.442 is towards the right of this 4, which was one of the roots. Okay, so the area above is equal to the area below. Question number 8. The first 6 marks in this question relating the definite integral with the area under the curve were straightforward. Only the best candidates were able to access the last 4 marks, with many struggling to explain the significance of the root 5.442. Most candidates gained all 4 marks in part A, which is good. Some unnecessarily complicated their proof by attempting integration by parts, but in the main, all calculations were accurately performed. As with all proofs, part B proved to be very discriminating. Many candidates picked up on the first mark for setting a quarter b to the 4 minus 2/3 b cubed minus 4b squared equals plus minus 20 over 3, but there was much confusion as to the sign of 20 over 3 on the right hand side. Remember, we talked about it should be negative because it's below the x-axis, because we're talking about integrals. Most candidates attempted to proceed by the method shown in the mark scheme. It should be noted that the division by b squared plus 4b plus 4 was much easier and faster than dividing by b plus 2 twice. Fully correct solutions to part B were rare, with many candidates picking 2 out of the 4 marks. In part C, many candidates realised that 5.442 was to the right of 4 on the x-axis and shaded an appropriate area, scoring 1 mark. Full explanations as to its significance were rare and confined to the best candidates. Any suitable statement that alluded to the fact that the area above the curve is equal to the area below the curve between -2 and 5.442 were acceptable. Question number 9. Given that A is greater than B and B is greater than 0, and that A and B satisfy the equation log A minus log B equals log of A minus B, we have to show that A equals B squared over B minus 1. So for this, for part A first of all, so for part A, we have log A minus log B equals log of A minus B, and subtracting logs with the same base, we have log of A over B equals log of A minus B. And if we anti-log both sides, we have a over b equals a minus b, and the rest is just GCSE level maths to rearrange for a. So we have a equals b lots of a minus b, so we have a equals ab minus b squared, and if we rearrange over here, b squared, that's equal to a lots of b minus 1. So therefore a is equal to b squared over b minus 1. Okay, now for part B, we have to write down the full restriction on the value of b, explaining the reason for this restriction. So first of all, we cannot take a log of a negative. Let's just quickly write that down actually. So we cannot take the log of a negative, and because of that, if we go and take a look at what we have over here for log b, well, the b can't be negative, so b must be greater than 0, and also a must be greater than 0. So therefore a is greater than 0 and b is greater than 0. Okay, so having said that, we already know what a is. We've worked it out over here. So in other words, because a is greater than 0, we have b squared over b minus 1 being greater than 0. So because of this, this bit is greater than 0, because remember, this all here is what a is. Okay, so from this, b squared, obviously that's greater than 0, and therefore b minus 1 must be greater than 0, because we have something greater than 0 divided by something greater than 0 must be greater than 0. So therefore b minus 1 must be greater than 0, because b squared is greater than 0, and therefore b is greater than 1. So therefore a, that's greater than b, which is greater than 1. Question 9, this was concerning logs. There were many good attempts to this question, though complete answers to part B were only achieved by the very best. In part A, candidates gained the first mark by writing log A minus log B equals log A over B, though a few did attempt to rearrange first and then use other equivalents. Candidates who gained this mark generally were successful at undoing the logs and making A the subject. Candidates who failed to recognise the logarithmic rule for subtraction or addition often made no progress with the question. It's quite a straightforward rule as well. Part B was more challenging, with many only scoring 1 mark. Many candidates focused solely on the exclusion of b equals 1 for the denominator and paid no heed to the condition that a must be greater than 0. Few candidates were able to provide a full explanation, including that since a is greater than 0, b squared over b minus 1 is greater than 0, and b therefore is greater than 0. Many candidates knew that the denominator of a fraction cannot be equal to 0, though few of them used the word undefined or infinity in their answers, but would more often refer to math error or cannot divide by. For question 10, for the first part, we have to prove that for all natural numbers, n squared plus 2 is not divisible by 4. Now, of course, when we talk about natural numbers, those are positive integers. Okay? Now, with positive integers, there's two cases which you have to consider. Either an odd number or an even number. And we will consider both in this question. So what I have over here then are the two cases which we need to consider, the even case and the odd case. So with the even case, if n is even, then we can rewrite n as 2k for some integer k. So replacing n with 2k, we have 2k all squared plus 2, so we have 4k squared plus 2, which is the same as 4 lots of k squared plus 2. So 4 lots of k squared, that's a multiple of 4, and then we add this 2. So a multiple of 4 plus 2, that's not a multiple of 4. And similarly, when n is odd, so we can rewrite n as 2k plus 1 for some integer k. Then we can replace the n with 2k plus 1, so we have 2k plus 1 all squared plus 2, so we have 4k squared plus 4k plus 1, and then we still have this plus 2. So we have 4k squared plus 4k plus 3, which is the same as 4 lots of k squared plus k plus 3. So we have a multiple of 4 plus 3, and that's not a multiple of 4. And therefore, for a set of natural numbers, n squared plus 2 is not a multiple of 4. Now for part II, given that x is a real number, the value of the mod of 3x minus 28 is greater than or equal to the value of x minus 9. We have to state, giving a reason, if the above statement is always true, sometimes true, or never true. Now, the statement in quotation marks which we're considering, that would be the following. We have the mod of 3x minus 28 being greater or equal to x minus 9. Now, if we attempt to solve this inequality, we first of all need to split this inequality up into two separate bits. So we have plus minus 3x minus 28 being greater or equal to x minus 9. Okay? So what we have over here then is, if we consider the positive bit, we have 3x minus 28 being greater or equal to x minus 9, and solving this inequality, we see that x is greater or equal to 9.5. And if we consider the negative bit, we have minus 3x plus 28, that's greater or equal to x minus 9, and solving for x, we see that x is less than or equal to 9.25. Now, if we were to add this on a diagram, we have the following. So in terms of the diagram, we've got this over here, we've got the mod of 3x minus 28. It crosses at 28 over 3 on the x-axis and 28 on the y-axis. We've also got the graph of x minus 9, that's shown in blue. Now, we have one solution, x is greater or equal to 9.5. So that would represent all this region here. And therefore, we've also got the other part, x is less than or equal to 9.25. That's all this bit over here. And that's where 3x minus 28 is greater than x minus 9. So therefore, hopefully you can see that the result is sometimes true. Okay? So the result is sometimes true. And that makes sense because the result is not true in between the 9.25 and the 9.5. So let's just write that down. The result is not true when x is in between 9.25 and 9.5, because then x minus 9 is greater than the mod of 3x minus 28. But we're looking at when the mod of 3x minus 28 is greater than x minus 9. Question 10. For question 10, this idea of proof is another new one in this updated specification. It was not well known, and a disproportionate number of blank or barely stated solutions indicated a lack of expertise in this topic. Candidates who scored full marks in the first part most often did so via algebraic proof, letting n equals 2m for even numbers and n equals 2m for odd numbers, although several candidates missed out on the final accuracy mark as they failed to insert a conclusion for all n. Weaker candidates tried to use m plus 1 instead of 2m plus 1 to represent odd numbers, and that's a GCSE mistake, although many candidates only consider whether either odd or even numbers but not both. Candidates who set out to use proof via contradiction tended to score few marks since they were unable to show understanding of how to use that method of proof. Proofs via logic were rare and tended to appear as part of a mix of different methods where the candidates seemed to be unclear for the best way to proceed. Some candidates seemed to think that using random numbers to show that the expression is not divisible by 4 amounted to proof, which received no marks. Remember, it's all algebraic proof you need to consider, and candidates need to be more precise, needed more practice on this style of proof. For the next part, more able candidates approached this problem algebraically rather than graphically. They were generally able to set up 2 equations or inequalities required, but errors often included in their use of algebra when attempting to solve them. Some candidates only set up one of the 2 required inequalities. Many candidates attempted the question by just substituting numbers into the expression, with the most of these deducing that the statement was always true. Where candidates drew a graph, they often did not describe why their graph indicated that the statement is sometimes true, and many graphs showed a line and a V shape but were incorrect in the relative positioning of these shapes. Question number 11. A competitor is running a 20-kilometer race. She runs each of the first 4 kilometers at a steady pace of 6 minutes per kilometer. After the first 4 kilometers, she begins to slow down. In order to estimate her finishing time, the time that she will take to complete each subsequent kilometer is modelled to be 5% greater than the time that she took to complete the previous kilometer. And using the model, for part A, we have to show that her time to run the first 6 kilometers is estimated to be 36 minutes 55 seconds. So for part A, we have the first 4 kilometers she's running at 6 minutes per kilometer. So we have 6 plus another 6 plus another 6 plus another 6. So what this is over here is her running for the first 4 kilometers a steady pace of 6 minutes per kilometer. And then after that, she takes 5% longer than she took to complete the previous kilometer. Okay, so for her next one, we would have 6 times by 1.05. So this is the 5th kilometer, and then for her 6th kilometer, we have 6 times by 1.05 squared. So what this is over here is the first 4 kilometers. This here is the 5th kilometer, and this over here is the 6th kilometre she runs. And therefore, the time would be, if we work all this out, we have 24, so that's 6 plus 6 plus 6 plus 6, plus 6 times by 1.05, plus 6 times by 1.05 squared. We get a result of 36.915, so we have 36.915 minutes. And if we convert this 9.915 into seconds, so let's subtract off 36 and then times by 60, we get 54.9 seconds. So of course we have something which is approximately 36 minutes and 55 seconds. Now for part B, we have to show that her estimated time in minutes to run the rth kilometre, for r being in between 5 and 20, is given by 6 times by 1.05 to the power of r minus 4. Well, for the 5th kilometre, we have 6 times by 1.05 to the power of 1. For the 6th kilometre, we have 6 times by 1.05 squared. For the 7th kilometre, we have 6 times by 1.05 cubed. For the 8th kilometre, we have 6 times by 1.05 to the power of 4. And we can continue this, but hopefully you will notice for the rth kilometre, we have 6 times by 1.05 to the power of r minus 4. In other words, whatever kilometre we're looking at over here, the power over here is always 4 less. So for the 5th, 4 less than 5, that's 1. For the 6th, 4 less than 6 is 2. For the 7th, 4 less than 7 is 3. And therefore, for the rth, that would be 4 less than r. So we have 6 times by 1.05 to the power of r minus 4. And that's quite important. So now for part C, we have to estimate the total time in minutes and seconds that she will take to complete the race. Now, for part C, you have to notice over here that she's running a 20-kilometre race. And what we have for the first 4 kilometres, she takes 24 minutes, and we discussed that over here. So for the first 4 kilometres, she takes 24 minutes. And that is exactly what we have over here. Okay? And now we're looking at the rest of the 16 kilometers, so to speak. Essentially, we're looking at the 5 to the 20. So for the 5th all the way up to the 20th kilometer, well, over here, because we're adding all these terms together, we're adding the 5th, the 6th, the 7th, the 8th, etc. all the way up to the 20th, we have over here, for the rth term, a geometric sequence. We can use this information to find the sum of a geometric sequence. So here, for the 5th to the 20th, we have the 5th plus the 6th plus the 7th all the way up to the 20th, if that makes sense. And for this, because over here we have 6 times by 1.05 to the power of r minus 4. We would have to consider a geometric sequence. Okay, so first of all we can find out our first term by considering what happens when r equals 5. So our first term a, that would be 6 times by 1.05 to the power of 5 minus 1. So if we work this out, 6 times by 1.05 to the power of 5 minus 1, that would be 5 minus 4. So let's just correct this over here, so we have 5 minus 4. That would be 6.3. The common ratio, r, that would be 1.05. And what we're doing over here is finding out what S16 is. So we are finding in this question S16. We're adding up all these 16 terms over here. So let's just put this in brackets. Here we have 16 terms, which is why we have this 16 over here, and we're adding them all together. So for a geometric sequence, that's given over here. So let's just quickly highlight this. So S16, that will equal the first term, 6.3, multiplied by 1 minus 1.05 to the power of 16 divided by 1 minus 1.05. And if we work this result out, so here we have 6.3 multiplied by 1 minus 1.05 to the power of 16, and on the bottom we have 1 minus 1.05. We end up with 149.04 etc. minutes. And therefore the total time t, that will equal the 24 minutes plus all these the rest of the 16 terms. So we add on this 149.04 etc. and working that out, so if we add on 24, we come out with 173.04 etc. minutes. We want our answer to be in minutes and seconds, so subtract off 173, times this by 60. So we have 173 minutes and 2 seconds. Okay. Question 11. Overall, very good attempts to this question were spoiled by a lack in accuracy. Part A was routine for most candidates, were thorough in showing their method. The most frequent and concise method involved calculations such as 24 plus 6 times 1.05 plus 6 times 1.05 squared. Occasionally the work was overcomplicated by candidates who converted to seconds, though the end result was generally satisfactory. Part B was found to be challenging, with candidates choosing not to answer. The most straightforward way to use was to use some values and spot patterns. This is a skill taught at GCSE, yet seemed to forgotten to many. Although many candidates knew that for Part C they needed to sum a sequence of terms, errors were frequent and many. A sizable minority lacked any appreciation of the model and resorted to the calculation shown here, 6 times by 1.05 to the power of 20 minus 1 over 1.05 minus 20. The majority of errors, however, were mainly due to a failure to link up correct values for a and n in the formulas for a geometric series. The most common of these was to use the strategy of 24 plus this result here, forgetting that the geometric sequence in this case should start at 6.3 instead of 6, and we discussed that. It is often a good idea in such a question to write out the first few terms in to gain an appreciation of the model and how the sequence is formed. From there it should be fairly straightforward. It should be a fairly straightforward task to write down this bit over here, and that should be 6.3 over here instead of 6. Question number 12. We have f of x which is equal to 10e to the power of minus 0.25x sine x, where x is greater than 0. We have to show that the x coordinates of the turning points of the curve with the equation y equals f of x satisfy the equation tan x equals 4. So for this question we have two different functions being multiplied by each other. We're looking at the turning points. That suggests to us that we have to find dy over dx and then set that equal to 0. So here, because it says turning point, that suggests to us we're looking at f dash of x, the first derivative, equaling 0. So for part A, we have so far f of x, that's equal to 10e to the minus 0.25 x times by sine x. We can let u equal 10e to the minus 0.25x, and we can let v equal sine x. U dash, that will equal minus 0.25 e to the minus 0.25x, and v dash, that's equal to cos x. So working out f dash of x, that's equal to v times by u dash, or we can have u times by v dash, don't make a difference. So we have 10 e to the minus 0.25x times by v dash plus u. So we have uv dash plus v u dash, so we add on sine x multiplied by minus 2.5 e to the minus 0.25 x. Okay, so if we tidy this up a bit, we have over here what's common to both. That would be a 2.5 e to the minus 0.25x. So we have 2.5 e to the minus 0.25x, and then we multiply that by 4 cos x minus sine x. Okay, and we're looking at where f dash of x equals 0. So we have 2.5 e to the minus 0.25 x times by 4 cos x minus sine x equals 0. Of course, 2.5 e to the minus 0.25 x cannot equal 0. So because this cannot equal 0, we have 4 times by the cosine of x minus sine x equals 0. So if we solve this equation, we can hopefully see that we have sine x over cos x equals 4, and therefore we'll write on a different line, and therefore tan x is equal to 4. Okay. Now for part B, figure 3 shows a sketch of part of the curve with the equation y equals f of x, and we have to sketch the graph of h of x against t, where h of t is equal to the mod of 10e to the minus 0.25t times by the sine of t, where t is greater than 0, showing the long-term behavior of this curve. Okay, so if we mod a graph, we reflect it in the x-axis, and it's quite straightforward to do. We have the following. Okay, so that's a diagram. Just been modded in the x-axis. Now for the next part of the question, the function h of t is used to model the height in meters of a ball above the ground t seconds after it has been kicked. Using this model, we have to find the maximum height of the ball above the ground between the first and second bounce. Okay, so if we're looking at the height of the ball between the first and second bounce, so there's the first bounce, second bounce over here, we're looking at this over here. So here is our first bounce, here's our second, we're looking at in between that, so we're looking at this point over here, and we're looking at the maximum as well. That's why we take the peak of this second. So we already know that the turning points of the graph from part A, that's given by tan x equals 4, and those are the x coordinates of the turning point. So using part A, so for part C, using part A, we have tan of t equals 4, and therefore t, that's equal to, well, here we have the inverse. Well, first of all, make sure that you're in radians. So let's just quickly change the angle unit. So we have the inverse tan of 4, that would be 1.32, etc. And then if we add on pi, we come out with 4.46, etc. And therefore, the value of t we require would be 4.46, etc. And this is for the bounce we require. Okay, so let's just add this in to our A. Okay, so with that, if we're finding the maximum height, we'd have to use this function over here to find the maximum height. So we're looking at h of 4.46, etc. So h of 4.46, that would be the mod of 10e to the minus 0.25 times by 4.46 multiplied by the sine of 4.46. And working this out, we have the mod of 10e to the power of minus 0.25 times by that value multiplied by the sine of this. It turns out we get 3.17, etc. So therefore the maximum height, that will equal 3.18 meters to 3 significant figures. Okay. And now for part D of the question, we have to explain why this model should not be used to predict the time of each bounce? Well, we have the following reason. So the model suggests that the ball will bounce an infinite number of times, but in reality, the ball will stop bouncing because of the friction between the ground and the ball. Question number 12. This question discriminated between all candidates of all abilities, with parts A and B more accessible to candidates compared to parts C and D. In part A, most candidates were successful at using the product rule and setting dy over dx equal to 0, though the latter was implied rather than being explicit in many cases. Missing the minus 0.25 factor when differentiating the e to the minus 0.25x was fairly common, but the differentiation was mostly carried out. A fair candidates failed to use the product rule correctly, instead multiplying the derivatives of each term, but these were in the minority. Having attempted the derivative, the majority did set the result equal to 0, possibly implied, and proceeded to cancel the exponentials. Reasoning for the cancellation was usually not given, but in this instance there was no requirement for such reasoning. However, it might be well noted that for such explanations many may be required under the new specification. Many candidates lost a final accuracy mark as they did not state or show division by cos x. Candidates need to be clear in a show that question, all steps need to be shown. Part B was the most successfully answered part of the question. Candidates realised that the graph of the mod of f of x should be above the x-axis. Where candidates did not gain full credit, this was usually due to poor drawing of loops, not decreasing heights, or rounding at the cups. A few candidates chose to draw over the original feature, which made it difficult in many cases to determine which pieces formed their graph. They would be well advised to sketch separate graphs in similar questions. There were less success in part C. Attempts at this part were varied, with a sizable proportion not making the connection with part A at all and attempting to find the value of h of t at pi over 2, or for some other value, or failing to substitute h of t, substituting into h of t at all. Many solved tan x equals 4 to find the acute angle, but did not look then for the further solution which was needed for the height between the first and second bounces, and so achieved only the first mark. In addition, use of degrees instead of radians was a common error, but this was allowed for the first method mark. The magnitude of their resulting answer should have alerted them to the fact that something had gone wrong. Part D was another part with a varied array of answers. Common incorrect responses referred to negative time, and that times between each bounce would be longer, or that the ball would not have bounced forever. Many candidates gave a root answer of the effect of air resistance had not been taken into account, or energy lost, or similar vague responses rather than relate to the context of the question. Since the model may have taken air resistance into account, the contributing factors to the model were not listed in the question. Such an answer was unacceptable. Question number 13. The curve C with equation y equals p minus 3x over 2x minus q lots of x plus 3, where p and q are constants, passes through the point 3, 1/2, and has two vertical asymptotes with equations x equals 2 and x equals minus 3. For part A, for the first part, we have to explain why you can deduce that q is equal to 4. Well, if we have these vertical asymptotes, with equations x equals 2 and x equals minus 3. We have an asymptote when either this bracket equals 0 or this bracket equals 0. And the reason for that is we can't divide by 0. So the way we figure out where the asymptotes are, we set either bracket equal to 0. And with this x plus 3, if we set that equal to 0, we find that x is equal to minus 3. And we know that for the other one, 2x minus q is equal to 0. We know that x is equal to 2. And with that we can find that q is equal to 4. So let's just write that down. For part A, for the first part, when x is equal to 2, we have 2 lots of 2 minus q equals 0 for our vertical asymptote, and therefore we have q equals 4. It's quite straightforward. And now for the next part, we have to show that p is equal to 15. Well, all we can do over here is substitute into this equation over here. So if we consider this coordinate of 3 and 1/2, we have over here 1/2 equals p minus 3 lots of 3 over 2 lots of 3 minus 4 lots of 3 plus 3. We're finding out what p is, so we have 1/2 equals p minus 9 divided by, well, here on the bottom we have 12. So if I multiply through by 12, we have 6 equals p minus 9, and therefore p, that's equal to 15. And knowing the value of p and q, we can therefore conclude y, that's equal to 15 minus 3x divided by 2x minus 4, because remember q was 4, and then we have x plus 3. And we have asymptotes when x equals 2 and x equals minus 3. Okay? So now for part B of the question, figure 4 shows a sketch of part of the curve C. The region R, shown shaded in figure 4, is bounded by the curve C, the x-axis, and the line with equation x equals 3. We have to show that the exact value of the area of R is a times by the natural log of 2 plus b times by the natural log of 3, where a and b are rational constants to be found. Okay? Okay, so to find this area, R over here, we first of all need to find the point where the graph crosses the x-axis. And we can do that by setting y equal to 0. So when y equals 0, we have 15 minus 3x divided by 2x minus 4 lots of x plus 3 equals 0, from which hopefully you can see we have 15 minus 3x equals 0, and therefore x is equal to 5. So we have over here the point x equals 5. Now we've got this curve C given by this equation over here, and for us to find out this area R, obviously we would have to integrate under the curve between 3 and 5, but before we do that, it would be easier if we split this up into partial fractions, and that will make our integration much easier to work with. So let's write that down and do that. So we will split up C using partial fractions. Okay, so if we split up C using partial fractions, we have 15 minus 3x over 2x minus 4 lots of x plus 3, and this is going to be equivalent to a over 2x minus 4 plus b over x plus 3. And if we multiply through by 2x minus 4 lots of x plus 3, we would have 15 minus 3x being equivalent to a lots of x plus 3 plus b lots of 2x minus 4. And the idea is over here to find the values of a and b. There's a couple of ways we can do it. We can compare coefficients, but the easiest way is to make these brackets equal to 0 to find the value of a and b. So for example, when x is equal to minus 3, we would have 15 minus 3 lots of minus 3. This will be equal to b lots of 2 times by minus 3 minus 4. The a bracket disappears, so we have 24 equals minus 10b, and therefore b, that's equal to minus 12 over 5. Similarly, when x is equal to 2, we have 15 minus 3 lots of 2, that's equal to a lots of 2 plus 3, so we have 9 equals 5a, that will be 9 over 5. And therefore, we can conclude over here that 15 minus 3x over 2x minus 4 lots of x plus 3, this is equivalent to 9 over 5, so we have 9 over 5 lots of 2x minus 4 minus 12 over 5 lots of x plus 3. And if you want, you can of course factorize out the 1/5 from both terms. So we have 1/5 lots of 9 over 2x minus 4 minus 12 over x plus 3. So what we need to do in this question is integrate under the curve between 3 and 5. So let's do that. So we need to integrate this equation here, this 15 minus 3x over 2x minus 4 lots of x plus 3. We need to integrate this with respect to x in between the limits 3 and 5. Okay, so let's just actually tidy all this up. And this will be equivalent to 1/5 lots of the integral between 3 and 5 of between 3 and 5 of 9 over 2x minus 4 minus 12 over x plus 3 with respect to x. Okay, so if we integrating, well, we still have the 1/5 on the outside, so we have 1/5 multiplied by, well, if I integrate 9 over 2x minus 4, if we adjust this, then we would have 9 over 2 times by the natural log of the mod of 2x minus 4 minus 12 times by the natural log of the mod of x plus 3. Obviously, we're looking for f dash over f. So we wish to evaluate this in between the limits 3 and 5. And if I multiply the 5 into the bracket, we would have 12 over 10. Sorry, no, we wouldn't. We would have 9 over 10 times by the natural log of the mod of 2x minus 4 minus 12 over 5 times by the natural log of the mod of x plus 3. And we're evaluating this between 3 and 5. Okay, so what we now need to do is substitute in for our upper limit and our lower limit. So for our upper limit, we have 9 over 10 times by the natural log of 2 times by 5 minus 4 minus 12 over 5 times by the natural log of the mod of 5 plus 3. For our lower limit, we have 9 over 10 times by the natural log of 2 times by 3 minus 4 minus 12 over 5 times by the natural log of 3 plus 3. Okay, so tidying all this up, for our upper limit we have 9 over 10, so we have 9 over 10 times by the natural log of, well, here we have 10 minus 4, which is 6, and then we subtract off 12 over 5, so let's tidy all this up, we have 12 over 5 times by the natural log of 8, so that's our upper limit. And for our lower limit, we have 9 over 10 times by the natural log of, well, we have 6 minus 4, which is 2, and then we have minus 12 over, we have 12 over 5 times by the natural log of 6. Okay, so if we simplify even further, we can rewrite okay, I need to make this a bit more clear. In the question, we were told that we want to show the area in the form a times by the natural log of 2 plus b times by the natural log of 3. So the way we can do this is as follows. For the upper limit, we still have 9 over 10, and what we can do with this is, actually no, we'll leave it as is. We have 9 over 10 times by the natural log of 6, and this 12 over 5 times by the natural log of 8, we can write as 12 over 5 times by the natural log of 2 cubed. Hopefully that makes sense as to why I'm doing that. And over here we have 9 over 10 times by the natural log of 2 minus 12 over 5 times by the natural log of 6. Okay, so hopefully so far so good. So if we power slide this 2 to the front, here we have 9 over 10 times by the natural log of 6 minus 12 over 5. Sorry, if I times that by 3, 12 over 5 times by 3, that's 36 over 5. So we have 36 over 5 times by the natural log of 2. That's our upper limit. Lower limit, we have 9 over 2. No, we don't. We have 9 over 10 times by the natural log of 2 minus 12 over 5 times by the natural log of 6. So combining these together, well, here we have 9 over 10 minus 12 over 5. That would be 33 over 10. So we have 33 over 10 times by the natural log of 6, and minus 36 over 5 minus 9 over 10. That would be minus 81 over 10. So we have minus 81 over 10 times by the natural log of 2. And the idea is over here, if you go back to the question, again, we want to express this in the form a times by the natural log of 2 plus b times the natural log of 3. And hopefully you can recognize 6 over here, we can rewrite as 2 times by 3. So we have 33 over 10 times by the natural log of 2 times by 3 minus 81 over 10 times by the natural log of 2. And when we multiply in the brackets, we add the logs. So we have 33 over 10 times by the natural log of 3 plus 33 over 10 times by the natural log of 2. And then we still have this minus 81 over 10 times by the natural log of 2. And combining these, we end up with minus 24 over 5 times by the natural log of 2 plus 33 over 10 times by the natural log of 3. And therefore, in conclusion, A, you'd find that to be minus 24 over 5, and B, that's equal to 33 over 10. Question 13. Only the strongest candidate scored all 11 marks here, with the majority losing at least 1 mark, usually the first mark in part A, or at least the last mark in part B. In part A, many candidates realised x equals 2 was linked to establishing that q equals 4, but they found difficulty explaining this by referencing the asymptote or the denominator being 0. Almost all candidates provided good explanations in the second part of part A, even when they had provided inadequate explanations in the first part. Part B, the vast majority of candidates knew that they used partial fractions to attempt to solve the question, with many achieving to the correct expression and correct integration. The most common error here was simplifying the final logarithmic expression, with many candidates leaving some of their answers in terms of the log of 3 over 4 or the log of 4 over 3, for example. It was uncommon, therefore, to see a fully correct solution in the required form. I think if you took your time in this question, it actually was quite a standard question in my opinion. Question number 14. The curve C in the standard Cartesian plane is defined by the equation x equals 4 times by the sine of 2y, where y is in between minus pi over 4 and pi over 4. The curve passes through the origin, or we have to find the value of dy over dx at the origin. Well, what we can do over here is, first of all, find out dx over dy and use the chain rule to find out what dy over dx is. So dx over dy, that will equal, if we work out what dx over dy is, well, via the chain rule, this will be 8 cos 2y. So we have 8 times by the cosine of 2y, and therefore dy over dx via the chain rule, that's equal to 1 over dx over dy. So we have 1 over 8 times by the cosine of 2y. And we're finding out the value of dy over dx at the origin. The origin, that's when x is equal to 0 and y is equal to 0. So at this point, dy over dx, that will equal 1 over 8 times by the cosine of 0. So we have 1 over 8. And next, we have to use the small angle approximation for sine of 2y to find an equation linking x and y for points close to the origin. So for our small angle approximations, we would have to use sine of theta is approximately theta. So for part B, using the small angle approximation, we have sine of 2y, which is approximately 2y. And therefore, what we can do is replace the sine of 2y with 2y. So we have x equals 4 times by 2y, which is 8y. And therefore, y, that's equal to 1/8 x. And for the next part, we have to explain the relationship between our answers to part A and part BI. Well, we have the following thing to say about that. So the first part A, that shows that the 1/8 shows the gradient of the tangent to the curve at the origin, and for part BI, y equals 1/8 x shows the equation of the tangent to the curve at the origin. And now for part C of the question, we have to show that for all points x and y lying on C, dy over dx is equal to 1 over a lots of the square root of b minus x squared, where a and b are constants to be found. Well, so far, we know what x is, that's equal to 4 times by the sine of 2y, and with this, we can use what we have over here, the cos of 2y, to find out an equation in terms of x. And we can do that via our non-trigonometric identities. So for part C, we begin with x equals 4 times by the sine of 2y, and therefore from here, x squared, that's equal to 16 times by the sine of 2y squared. And therefore, the sine of 2y squared, that's equal to x squared over 16. And one of our known identities, we have sine squared theta plus cos squared theta being equivalent to 1. In other words, what could we say from here? In other words, sine squared theta, that's equivalent to 1 minus cos squared theta. So we can replace the sine squared 2y with what we have over here. So in other words, think about this. Well, actually, we can find out what cos squared theta is. Cos squared theta, that's equal to 1 minus sine squared theta. So in other words, cos squared 2y, that's equal to 1 minus sine squared 2y. And we know what sine squared 2y is, that's x squared over 16. So this over here is the same as 1 minus x squared over 16. And therefore, we can state what cos 2y is. Cos 2y, that's equal to 1 minus x squared over 16 square rooted. Okay? And in the question, we have 1 over 8 lots of cos of 2y. And we wish to express this in this form over here. And notice over here, we just have an x squared. So we can adjust what we have over here in an equivalent form. So if I factorize out a 1 over 16, we have 1 over 16 lots of 16 minus x squared square rooted. And so we can split this up. We have 1 over 16 square rooted times by 16 minus x squared square rooted. And 1 over 16 square rooted, that's 1/4. So we have 1/4 lots of 16 minus x squared square rooted. And we already know that dy over dx, that's equal to 1 over 8 times by the cosine of 2y. So we have over here 1 over, let's do this neatly, so we have 1 over 8 times by 1/4 lots of 16 minus x squared square rooted. 8 times by 1/4, that's 2. So we have 1 over 2 lots of 16 minus x squared square rooted. Okay, so that's our final answer. So the constants a and b, those would be 2 and 16. So a equals 2, b, that's equal to 16. Question 14, examiner report wise, a small number of candidates did not attempt this question. Whether this was due to a lack of understanding or due to time constraints, that's unknown. Part A was generally done well with a surprising proportion using implicit differentiation. Don't know why you do that. A good number who found dy over dx correctly failed to substitute in y equals 0 to find the value of dy over dx at the origin. Candidates who tried to expand sine of 2y using the double angle formula and then differentiating using the product rule often went wrong. That's so much work for 2 marks. The small angle approximation in part B in the first part was also well handled. More settled for the form x equals 8y, although some rearranged to y equals something, and that's what I did. Many marks were generally lost when sine of 2y was replaced by 2 theta instead of 2y. Many candidates failed to see the link between part A and part BI, even though they had both answers were correct. They were unable to see that the gradients were the same, or else failed to explain themselves coherently. Only a small percentage of candidates were able to secure full marks for part C, and it was not uncommon to see the whole question left unanswered. This type of question was common on the legacy core maths core 3 paper, so if you have a look at those, you probably would have answered the question quite well.